how we use current experiences to reconstruct and update our memories. She draws on a broad variety of methods in her work, including neuroimaging methods, behavioral experiments, and computational modeling. And in addition to being trained as a neuroscientist, Asieh has earned an MD, and she also studies populations with psychiatric disorders to understand compensatory mechanisms that support adaptive behaviors. So today she'll be presenting her work titled Bridging Past and Future, how neural representations of events are encoded, recalled, transmitted, and updated. Please join me in welcoming Dr. Asieh Zadbood.
Asieh, I think you're muted.
Oh, yes.
Asieh, you're muted. From the top.
Sorry, I couldn't unmute myself for a second. So yeah, thank you for the nice introduction, and thanks everyone for being here today for this talk. So I will begin by talking about our daily life experiences in which we are encountered with a stream of information, and that they are usually life events, and they do not occur in isolation, and they are kind of related to each other. So in each moment in time, our brain is involved in dynamic and interactive processing to bring the present and past data to be able to support adaptive behavior. So in each moment in our life, our brain is not just processing and encoding the present information. It also uses the past memories to better understand the future. So to better understand the present. Neural mechanisms that, for instance, when we see Santa in the street, we also basically use our prior memories, from seeing Santa in a movie or in the streets before, and our neural representations are not a mirror reflection of what we see right now. Previous research also has shown an important role for encoding, an important role for prior knowledge in encoding memories and in a dynamic construction of basically neural representation during encoding. Sorry, I have a problem with the slides here. Okay, it's resolved. Yes, cool. Sorry for the interruption. So when we remember past events, the representations related to those events are being reactivated. But we don't retrieve memories as carbon copies of the original experiences. They are being reconstructed. Our brain may alter or fill in some information, for example, when false memories are formed, but changing memories is usually an adaptive process in service of improvements in the behavior. And I will elaborate more on this during this talk. Also, it has been shown that the act of remembering itself makes past memories susceptible to change through a process called reconsolidation. Construction happened next when transforming our thoughts into concrete sentences and used language to communicate memories, selecting which parts of the past events we should include in our the speech, and when we are talking to other people is highly influenced by past episodic and semantic memories. We use prior knowledge to compress, alter, optimize, optimize the stories to be more clear and coherent. Also, the person who is listening to us uses their prior knowledge to rebuild and imagine the story in their mind. For example, someone without any prior knowledge about Santa will not properly understand our recount about an earlier movie or an earlier encounter with Santa. This communication is a constructive process both for the speaker and for the listener. You might also receive new important information, in this example through this friend, that leads us to mentally go back in time and explicitly update our memories based on the most accurate interpretation of the event. Updating of prior knowledge based on new information is a reconstructive process. And all of these processes also influence the future. Like first, they influence how well we remember the events in the future. Many studies have shown the role of encoded conditions on subsequent memory. Our prior experiences enable us to build predictions about what happens in the future, and we can also like mentally imagine the future as a like big picture, like involving like many scenes and like events. So these constructive processes make a bridge between past and future, and the question that I like try to address partly in this talk is that how does the brain support these reconstruction or reconstructive processes? I tackle this question by asking two more specific questions that I will address during this talk. First, I ask, are there no shared neural mechanisms underlying encoding, recall, and imagination of events transmitted during communication? And then I ask that how do neural representations of events are updated to incorporate new critical information? Like starting with the first question, in which I ask how memories of past events, for instance, during recounting a recently watched movie to a friend, are formed and transmitted to other individuals. Basically, to test this question, we have 18 participants that watch a full-length movie in the scanner. So here's an example of like what they watch. So then one of these group of viewers that we call here the speaker recalls the movie in their own words again in the scanner. So for instance, for this particular scene, this is how her recall looks like.
We're not getting your audio, unfortunately.
Okay. Okay, so I will just skip this part. This person is like basically talking about like what happened in the scene and just describing that like he felt and like he kind of with magical like some magical effects like pushes the like bed and things like that. So here is like the like behavior of this person. Like this speaker. So this thing that we watch would be like one of these boxes that we see here. So each box is a scene, and y-axis shows how long this scene was in the movie, and the x-axis shows how long it took to recall it. So we already see some evidence of construction through compression in events, because some of these tall events means that like it took like less amount of time for people to recall like those scenes comparing to the time that it took for them to watch it. So lastly, we have a group of 18 people that are naive to the movie. They have never watched this movie and they have no information about this movie, and they just listen to the speaker, to the recall that was done by this one speaker in the scanner. So by this task, we create a circle of communication through encoding, retrieval, communication, and imagination. We approach our question about neural mechanisms underlying these functions by looking for shared event-specific neural representations. If we assume the information is successfully transmitted through this cycle, we might be able to track shared neural patterns across all these three conditions. So how could we look for shared neural representations? We need to compare the brain responses in different people, because people who perform the task in our case across our communication cycle are different. We need people who watch the movie, and we need people who are actually naive to the movie, and we want to compare them. this basically question or this problem has been solved by intersubject correlation, which is a method that allows us to measure synchrony across different brains. It has been shown that people, for instance, watching the same movie show strong correlation in the time course of their brain function during viewing. But in our case, we would also like to compare the brain response across encoding and recall, and these two conditions are from different modalities, and time points by time point information is different between them. So to overcome this issue, we use a method proposed by Chen et al. That I will explain in the next slide. So for the analysis to compare the brain responses during movie viewing and recall, we have basically we have different stimuli from different modalities, as I described. What we do is that imagine that each color on these two time courses is one of the events in the movie. What we do is that we average the time course of brain response within each scene, and then we compare the patterns of brain response for that scene in the movie to the pattern of brain response to that same scene in the recall. So we do this through a searchlight. It means that our pattern is consistent with the voxels in each cube in the searchlight, and then to obtain the baseline of this similarity, to calculate the significance of these correlations, we use a permutation method in which we compare basically random non-matching scenes to get a baseline. So here we ask if, as the first step, we ask if event-specific neural representations are shared between encoding and recall. This this question has been previously studied by Chen et al. And we successfully replicate their findings in the default mode network. So here's the results. As you see, there's a strong neural pattern similarity in 4 regions of DMN, including MPFC, angular gyrus, and proteins. And the bar graphs that you see on the lower part of the figure, they are basically correlation values between matching scenes in red and non-matching scenes in blue. And this shows that the similarity we observe is scene-specific and actually links corresponding scenes in encoding. So then we ask that are event-specific neural representations transmitted to the listener's brain via communication? Related to this question, previous work by Stephens et al. Has shown coupling between speaker and listener in the temporal domain, meaning that when they actually compare the entire temporal time course across listeners and speaker and listener. Here we basically show this coupling in the spatial domain. We extend this previous finding to the spatial domain, and we show that speaker and listener share event-specific neural representations in the default mode network. So lastly, here comes the most novel part of the study that directly links encoding during watching the movie and imagination of movie scenes. We ask if the event-specific neural representations are shared between viewers and listeners. Interestingly, we see a strong and significant similarity between the neural representations across these two conditions. And this shared representations are modality independent, because these people, one of them, they just listen to the story in a different language than the movie, and the other one just watched the movie. And they're constructed from smaller amount of, in the listener's brain, they're constructed from smaller amount of information transmitted through language. So it kind of implies that listeners sort of experience the movie without actually watching it. So to kind of have a quick summary of this part, we ask, are there shared neural mechanisms are there shared neural mechanisms underlying the encoding, recall, and transmission of information via communication? We kind of introduced this communication cycle, and we showed that patterns of brain response are shared within this cycle. So we showed that these shared patterns are observed in the default mode network mainly, and also we showed that there's intimate correspondence between memory encoding and event construction or imagination. And by providing evidence for shared spatial neural patterns across encoding and imagination, these findings extend prior research that suggests DMN is involved in processes that entail construction, such as memory encoding, retrieval, future planning, mentalizing, and self-construction. So then we will move to our next question, in which we ask how do neural representations of events are updated to incorporate new critical information. So imagine a child that believes in Santa and thinks Santa brings Christmas gifts. So one day during a conversation with their friends, they realize that Santa is actually not real. So this information leads to a lot of changes in their memories. Now remembering a memory of Santa in the streets in the past was sadly sitting like down. Like now it makes sense because now she knows that he was actually like a normal human. Or like all the gifts that were supposed to have been from Santa, now she thinks that maybe they were from maybe her parents. So we actually want to know that how this process of memory updating happens in the brain in cases like this, that we get new critical information about the past and we want to go back in time to kind of update our memories. So to investigate this question, we use the Sixth Sense movie. So I have a spoiler alert here because I need to describe the story to be able to describe the paradigm. So maybe if you haven't watched the movie, mute your sound until like the spoiler alert text goes away. So yeah, the story is about a child psychologist who is treating a kid that thinks he sees ghosts. Everything looks like a normal psychologist-patient situation, but at the end of the movie, there's a huge and dramatic twist in which we realize that the doctor was in fact one of the ghosts the kid was seeing throughout the movie. After watching the movie, participants do a cue recall task of the movie scenes in the scan. So basically, we give them short snippets of the beginning of movie scenes, and we ask them to describe the rest of that scene in their own words, and we basically record the brain response and the recording and the results of the story. So participants recall all the scenes in the movie, but we hypothesize that the effects we expect will only be seen in a selection of scenes in which the twist information dramatically changes the interpretation of those scenes. For example, there are scenes that it seems like the wife of psychologist is cheating on him. After watching the twist, we realized that she was trying to move on from her grief and start a new life. So my point is that like the importance of these scenes in terms of how much they are related to the twist information is different. So some of them we hypothesize that we see the hypothesized effects. So the main group in our experiment watched the movie and then watched the twist scene, which here I have shown as a yellow block in between the encoding and the recall. So they watched the movie thinking the doctor is alive, and that I show as a D index for doctor and the blue color. So if memory updating happens, they now recall the character as a ghost that we index with G and the red color. The second group watched the movie, but we spoiled the movie for them at the beginning. So they watched the movie knowing the doctor is dead and is a ghost, and recall it with the same ghost interpretation. So these boxes are both red. Our last group watched the movie, but we cut out the twist scene. So they watch and recall the movie thinking the doctor is alive and actually like a doctor. So these boxes are both blue. So this group of people, when they come out of the scanner, I played those last scene that we had cut out of the movie for them, and they were like really surprised and like kind of showing a lot of like surprise and kind of immediately starting to think that what that scene like that I saw in the movie, so that this is what they meant, and this is actually the exact process that we expected to happen in the scanner for them, so that they start to mentally go back in time and kind of update their memories. So, as I suggested, and like other research suggests, encoding is basically a constructive process based on prior knowledge. So the question that arises here is that do differences in prior knowledge then affect neural representations of events during encoding? So previous research suggests that the difference in perspectives before listening to a story makes the brains of the two groups distinct in the default network. So here in our three groups who watched the movie, two groups watched it with the same prior knowledge, two groups that are shown in blue, and they thought the doctor character was in fact a doctor. So based on our hypothesis, the neural representations in these two groups should be more similar to one another than the neural representations in twist and sport group that had different prior knowledge about the movie. So one group thought that the doctor was a doctor, and the other knew that he was actually a ghost. So based on our findings in the previous studies, including the study that I described, and our research and other research showing the role of DMN in constructive processes, we focus our analysis on default blood network here. After averaging time course within each scene, we calculate spatial intersubject correlation as I described before for each of these two comparisons. These two white arrows each show one of these correlations that I'm talking about. And then we compare the strength of correlations in each of the MNRIs. The basis of our computations is very similar to what I described in the previous study, so I don't go into the details here, but I'm happy to answer any questions about the methods afterward. So also the effect of the twist, like I mentioned, on the interpretation of the movie scenes was not the same. So before the analysis, we selected 7 scenes that their interpretation would dramatically change after realizing that the doctor was in fact dead. So this was kind of rated by independent raters, like which scenes you think have the most change by the twist, would have the most change by the twist. So we basically use these scenes in the mean analysis that I described later. So here is the result of our analysis for this condition, basically comparing these two white arrows, and like the difference between these two correlations is like shown on the maps. So basically these are the maps that show a higher correlation for the encoding in the twist and no twist condition comparing to the encoding in the twist and the sport condition. So this map basically tells us that these regions are sensitive to changes in the interpretation of the movie during encoding, and this map basically tells us which DMN regions show the predicted difference in the strength of correlation that was schematically shown as different size of those arrows. And like significances on these maps are corrected for multiple comparisons. So, sorry, I was just checking the charts. Okay, next we go to the recall condition. We expect memory updating to happen in the twist group, as I described before. So this group watched the movie thinking that the doctor is alive, and then watched the twist before doing the recall. We hypothesized that the twist information begin an update in the neural representations of the events. So analyzing the recall behavior shows us that information are indeed integrated, the new information are indeed integrated in the recalls of the story in this group. So this gives us like kind of more confidence that the process that we had in mind is actually happening. So then we ask that recall neural representations reflect the change in the interpretation of the events. So if this happens, the recall of the twist group should now include ghost representations. So now it becomes red, and based on this hypothesis, now it should be more similar to the recall of the sport group, and less similar to the recall of the third group, which are naive to the twist. And this is basically, in fact, what we find in the RIs that I'm showing here. Mostly you see that NPFC and also percutaneous, they're showing this effect. So to find out which regions were showing the effect in the expected direction during the encoding and during the recall, we calculated the interaction between the encoding and recall effects 15 regions in the default mode network, as shown here, show a significant interaction between these two conditions. So to further confirm that in fact these differences, these effects emerge due to the changes in the interpretation of the movie, we calculate this analysis 2 more times, once including all the scenes that once we're including all the scenes and once including non-critical scenes. So the graph shows each of these 15 ROIs on the x-axis and the interaction index on the y-axis. Blue represents the calculations, including the critical scenes, and you can see even by looking at this that across all ROIs, interaction effects are larger for critical scenes. And this confirms the importance of scene contents in the effects that we are observing here. So, So lastly, to further investigate how neural representations during a recall reflect the changes in the interpretation of the events, we run a comparison across encoding and recall. So we hypothesize that if recall representations reflect the memory updating, now they should be more similar to the spoiled encoding of the movie compared to the naive recall. So the predicted, so this again here, the difference between these two arrows is the prediction or hypothesis that we have. So we ask, do the recall neural representations reflect the change? And here we ask this in a different way by comparing between encoding and recall. And what we see here is basically a selection of, again, DMN regions, including angular gyres, that basically show the effect in the hypothesized direction. So in using this study, we showed that prior knowledge altered the neural representations during encoding in DMN. And we showed that twist information transformed the neural representations of the encoded information during recall. Also, we showed that different implications of DMN regions across different but related processes exist. And I'm happy to discuss these differences that we see in the which regions of DMN are involved in which process in more details later. So after these two studies that I described in details, I wanted to kind of also briefly go over basically some other studies that I'm running right now. So by these two studies, we kind of show the spatial role for DMN in these constructive processes. So one of my ongoing projects is basically measuring parent separation and parent completion. So the ability to use past knowledge to make mnemonic judgment is critical to support constructive processes. So I have studied, in this project, I have studied parent separation and parent completion in schizophrenic patients with delusions and healthy controls. And we basically hypothesize that these processes may be occurred in individuals with delusions, and we also look for compensatory mechanisms that enable us to actually perform these tasks. So another line of research that I pursue is basically looking at reactivation of memories and replay of memories, which again I see them as connected to my bigger picture of constructive processes. So basically reactivation of memories is also a constructive process, which memories from the past we select to remember or replay or reactivate. It depends on prior knowledge, depends on many factors. And this is what I study in these projects. So how does replay affect the face of memories? Also among the questions I asked in a couple of ongoing studies about memory activation. And lastly, what I described before, these processes, they all influence the future. One of the important factors in this in here are how these processes in the current time help us make predictions. So for instance, if based on what we know about Santa and everything, if we see a scene like this is what kind of incongruence with what we expect to see. So this will be kind of we already have a prediction that here this would be violated. So in my research, I studied that how does prediction error affect encoding and how it kind of retroactively changes memories. So basically here is like the slide that I'm sharing. So thank you for your attention, and thanks to my mentors and collaborators at Princeton and Columbia. So the data sets for both of these projects are uploaded on OpenNow, so you can go and find them by their name or by looking up my name. And basically you can use the data to these scans to kind of ask other new questions in this in the same domain. So I'm happy to answer to your questions. Thank you.
So if you have any questions for Dr. Zadbood, you guys can post them in the Q&A, and then I can ask them for you.
I also have a quick question, I guess, maybe to get the ball rolling.
That would be great.
So I was interested in your, in the first set of results you were showing where you had the similarity in the spatial inter-subject correlation, I hope I'm getting that right, between the viewers and the listeners of the story. Mm-hmm. And I'm curious whether you saw any of those correlations in visual cortex, like for example, scene selective regions, or how much were those correlations constrained to like higher level default mode kind of regions?
So that's like like a lot of this is actually constrained to higher level regions. We might see, I didn't do like a kind of ROI analysis for like visual, like high level visual areas, but for sure we didn't see like lower level, low visual areas to be kind of showing these effects. And that's one of the points about like this result, that we kind of show that it seems that this is kind of a high level effect, kind of beyond the like sensory regions. But yeah, higher level like visual regions, I think I have some of them on the maps, but I haven't done like analysis.
Yeah, like one thing, I guess, quick follow-up with that would be, I'd be curious if people, like, so, there's a lot of variance in how much imagery there's strength of imagery that people report. And I'd be curious if, for participants who report having stronger mental imagery, if maybe when they're hearing the story, they have, like, more shared visual cortical activity with somebody actually seeing the story is just something I think.
Yeah, that's a really good point. Something, for some reason, in my like practices, my talk was getting too long, so I kind of removed some of the like results, but now I feel like that kind of got like too short. But one of the like results that I didn't include is not directly related to visual cortex, but it's about like the experience of like these like listeners. So these listeners, they had, after they came out of the scanner, they had like a memory test, like a full recall from what they remember from the movie, and through a kind of analysis that it's hard to describe without this slide and going through details, but we kind of showed that they seem to have some particular connection to the speaker's brain, so the ones that they had higher memory score, better comprehension of like the movie. It seemed like that they also kind of saw the movie or like through the lens of the speaker, which is kind of something that, yeah, it's included in the paper. You can check later.
Okay, we have two more questions so far. So the first is, can you elaborate on what might be the correlation between a default mode network activity and imagination, depending on creativity? So, for example, would it be different or more enhanced in individuals considered more creative than others?
Yeah, that's a very good point. I don't have like research on top of my mind that like kind of targets like creativity. Like there has been like previous research that looked at like for instance scene construction, like asking people to like imagine that for instance they are at the beach and like you know it's like a sunny day and things like that, and they show that like DMN is actually like involved in like when people are actually engaged in this process. But that's a good point. I don't remember that if those studies they have any like any measure related to creativity, that how basically how well people like elaborated this in their mind. But that would be like yeah, that would be a great next step to ask, and that could be also like correlated to like other measures of creativity for that each person, like you know, like outside the context of like that task, like you know, there are other ways that we can like measure how someone is more creative than others. But we can look at the correlation with these effects, and that would be super cool.
Thank you so much. That question was from Summer. And now another question is, would you expect the results to change if the original memory were consolidated? So for example, if they are spoiled, I think this means if the if the results of the ending is given away 1 week later before rather than before / after the actual movie. So do you think a short-term prediction error affects updating differently than a long-term prediction error? So for example, longer study prediction error delay and therefore reconsolidation process instead.
Yeah, that's a great question, and that's one of the things that I was like thinking about when I was designing the study. So originally I was considering like having a like long-term like you know condition for the study. So I mean that we would like do like the same as your suggestion, that like you know you could imagine that they you could imagine two conditions, so they could get the prediction right after the movie, but then we allow enough time for consolidation before we ask them to record the movie, or they could watch the movie and not watch the quiz, and then after like a week of consolidation they watch the quiz and then they do the record. And yes, I think that the results would be kind of would be different, because like the difference here is that you know I think like the memories that are consolidated, it would be like, you know, the process of changing them would be different compared to these memories that are very short term. But unfortunately, because of like limitations in terms of like the time we had, and we already have like 3 groups, more than 60 subjects, you know, so it would be too much of like a big project to incorporate that condition. So that I kind of left for some future like steps, and it hasn't happened here. But if anyone follows up with that condition, I think that would be like super cool.
Thank you so much. If anyone, maybe I'll give it like another 15 seconds to see if someone else posts a question. And if not, thank you so much for this amazing talk and for joining us. We really appreciate it.
Thank you for
And the other thing is, so we'll have a Q&A after this for postdocs and trainees. So I'm going to put that Zoom link in the chat right now. Oh,
Recording
sorry.
stopped.
I said postdoc and trainee, but you know, postdoc and trainee Q&A. There's the link. So yeah, so we can give this a few minutes if there's any more questions, and if not, then we can switch to that other Zoom room.
All right, I'm gonna go ahead and end the webinar, so let's switch over.
Cool, sounds
Okay.
good.